Hi, everyone. Good morning, good evening to all of you. I am Yashima and I will be moderating the session today. It is the fourth simulation training. So by now you must be aware how important it is to right size your HVAC system. So today we will learn about how to evaluate the air conditioning loads in your building and how you can use your load calculations for system sizing. Our experts will also explore the energy savings through various types of HVAC systems and demonstrate how to model a unitary system in your building. Before we begin, I would like to acknowledge the support of Department in Science and Technology and the support of all our affiliates. Okay. Just a second. Yeah, there was some issue with my slides there. I'm so sorry. Yeah, Prasad, can you confirm if my slides are correct?
Yeah, they are good.
Okay. All right. I'm so sorry about that. We have with us today Mansi Parekh and PC Thomas. Mansi is a senior sustainability consultant and has key qualifications in the field of passive design, new energy cooling and HVAC systems. She has worked on various projects with goals leading to net zero energy, water and waste. We also have with us PC Thomas. PC is the founding director of Team Catalyst and also is an adjunct associate professor at the University of Sydney. He specializes in integrated building design, using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. PC is talking to us from Australia, so it is late evening for him right now. Hi, PC. Hi, Mansi.
Hi, Yashima. Hello, everyone.
Hi. Hi. So we will first begin with your presentation, Mansi, followed by a quick Q&A since you have to leave a little early, and then we will start PC's presentation. Over to you.
Yes. Thank you, Yashima. So I'm going to start projecting my screen. Yashima, will you? Can you see my screen?
No, nothing yet.
Let me know once you have something on your screen.
Yeah.
Can you see?
No, nothing, Mansi. Yeah, okay. It's coming up now.
Is it? Perfect.
Yes.
Okay.
And but it's some slide in between, not your first slide.
Okay.
Yeah.
Oh yeah.
Now,
So,
y-
oh,
n- yeah.
okay, perfect. So, hello everyone. In today's webinar, we'll be discussing about internal and external loads in building, assumptions for energy model, and cooling loads reduction through load calculation. So, what are so in previously we would have heard I mean we would have heard the term HVAC loads. So, what are HVAC loads? So, HVAC stands for heating, ventilation, and air conditioning loads. In most part of India, space cooling is predominant. In buildings, considering our climate conditions. So cooling loads, hence we require cooling loads specifically. And cooling loads is the rate at which sensible and latent heat must be removed from the space to maintain a constant space temperatures. So, set point temperatures or dry bulb temperature and humidity in a particular space. So, those are called HVAC loads, or specifically in Indian climate, we would call it cooling loads. Since, temperatures or climates like Delhi, say Ahmedabad, would specifically require a lot of cooling across the year. So in those, there are two kinds of HVAC loads. First is external loads and internal loads. So as you can see in this particular diagram, we can see, we will be exploring the external loads in the building. So they are specifically dependent on the local climate factors like solar radiation and dry bulb temperature. Yashima, we have a question coming up. Could you? Uh,
Yeah.
what's it?
Right. Here's the question. So, what are HVAC loads? Are they external loads or are they internal loads? Okay, I'll we're getting many responses. Actually, I will now go ahead and end the poll. Here you go, Mansi.
So I believe most people have answered D, which is occupancy gain. Correct, Yashima?
No, the answer is internal loads. 67% have answered internal loads
Internal load.
and 33% have answered external loads.
Okay, perfect. So
Are you not able to see the poll, Mansi?
no, somehow I'm not able to see the polls.
Oh, okay.
Sorry,
So,
Mansi, if I can just say the question that was there was what are HVAC loads? A single choice answer, and it was external loads and internal loads were the two options.
I
Yeah.
think
There may be some
question
confusion because of that.
yeah, there's a confusion with the question. Okay, in that case, there are two kinds of HVAC loads. Okay, there are internal loads and external loads. So say the question was supposed to be, which are not external loads. So for example, was conduction through walls and roofs, conduction through, glazing, conduction through ventilation, so infiltration gains and occupancy gains. And the
Yeah,
answer was
I have
supposed
launched
to
that
be,
question now. Hang on, Mansi.
okay. All right. Oh wow! I hope they haven't seen the answer. Yashima, should we end the poll?
Yeah, I am now ending the poll. Here you go, Mansi.
Okay. You'll have to tell me the results, unfortunately, today.
Okay, so 76% say occupancy gain, 11% say ventilation or infiltration, and then 7% say roof wall conduction.
Okay. All right. So most of the people here has given the correct answer, that is occupancy gains. Okay, so as the definition, or say as that's built in the word, which is called external loads, so external loads are the heat gains through envelope, which happens due to the external factors, which are specifically predominated by climate. you know so external loads are loads which includes conduction gains through walls, glazing and roof, and radiation gains through roofs and glazing. We all know that there are three predominant types of gains in an envelope. That is through conduction. So heat transfer happens through conduction, convection and radiation. So conduction heat transfer generally happens through your walls and the roof. Radiative heat transfer predominantly happens through the roof and roof and the glazing, and conduction again happens through glazing too. So uh, so that's the reason. So those are all external loads because they are predominantly dependent on the envelope and the external factor. So external loads varies across the day and across the season. So say for example, the radiation gains through windows will be maximum during the typical summer day from say 11 a.m. to 3 p.m. Because irradiation is quite high during those times, and it would be say radiation gains again would be almost zero because sun sets after 6 p.m. or 5 p.m. during a typical day. So your external loads vary across the day. So a well-designed envelope can intervene to reduce the envelope loads. This can be done through efficient walls, roofs, insulation, and glazing with a lower U value and SHGC. So say for better glazing, better quality glazing with a DGU of U value of 2.2 and SHGC of 0.27, and a proper shading, the energy efficient shading design would help you to cut down your external loads. So then there are certain checks which would help when you start, building the energy model. There are certain checks where you could see that, if your external loads are meeting the requirement or if they are exceeding a particular threshold for energy efficient building, you could check Griha benchmark, where they talk about the peak cooling loads in terms of these. So yeah, as you can see, these are all external loads. Uh, the next is these are the internal loads. So these, as the name suggests, these are the internal loads and based on the internal components of the space. So Yashima, we have a question up.
Yeah,
So if you project that, if you could start the poll.
yeah, I am
So
launching that now.
perfect.
So the question is, what are not internal loads? And the options are occupancy load, lighting load, equipment load, and conduction gain through walls. There's a typo there. It's not conduction, it's conduction. I'm sorry.
Yeah.
Not on your slides, Mansi. It's in the
Yeah,
Zoom
I saw that
question.
on the poll. Yeah.
All right, another 5 seconds and then I'll close the question.
Mhm.
Okay, I'm now ending the question poll. Mansi, here are the results. So 7% say occupancy, 6% say lighting, 4% say equipment, and 84% say conduction gain through walls.
Perfect. So I think 84% of the people are correct. So the conduction gains through the wall is the correct answer. Those are not the internal loads. So internal loads come from the heat generated by people, lighting, and equipment inside the space. Lighting and most equipment loads are sensible loads. There are again two kinds of loads. One is the sensible heat, and the other is the latent. So lighting and equipment mostly are sensible heat gains, while metabolic heat generated from people are a combination of both sensible and latent fuel. So you can get specifically this information, occupancy gains reference from ASHRAE 90.1. You could refer to lighting gains or from the fixture details from a particular manufacturer. Uh, and say, there are certain and equipment gains you can also get from the manufacturers. So lighting gains can be reduced by using LED lights. Those are very energy efficient, and equipment gains can be reduced by using BEE 5-star rated appliances. So there are BEE stands for Bureau of Energy Efficiency. that so they have the star rating system, which generally rates appliances like fans, fridge, air conditioning units, etc., etc. So when we are selecting the equipment, it is important that we start looking into more energy efficient building equipments, which are star rated. So the next step when we start building a energy model, the first step which I generally take when I start constructing or building an energy model in any particular software is thermal zoning the space. So thermal zone is a space or a collection of spaces having similar space conditioning requirement, and and they have similar sort of set point temperatures. Okay, and these are the basics and these are the units for building an energy model. Okay, so there are two sort of types of thermal zone. Uh, one is the perimeter zone and the other is the core zone. So as you can see in the figure here, that if this is a square plate, okay, then we have perimeter zone on all the four sides. The depth of perimeter zone generally is from 12 to 15 meter. This is we have four zones because irradiation on the sun on all four directions will be different. So say north, it would irradiation of the sun on the north would be different as compared to south, correct? So the external loads would be different in all of these four zones, and we have four types of perimeter zone and one core zone. So where uh, the impact of internal loads will be very high, as well as compared to in perimeter zone, the impact of external loads, as we saw that climatic parameters would be very high. So say these type of thermal zones are used for indoor HVAC system sizing. Indoor units. When you have say VAV systems outdoors, and we have cassette units. Each of these space would have a indoor unit. So say for example, if the perimeter zone, say perimeter zone 3, which is facing south, might require 2.2 tonnage of refrigeration. The indoor unit in north might require 1.8 TR, while the core zone would require 1.5. This is again an assumption. This would vary from case to case, but there is uh, definitely a difference seen because if the external loads are predominant in a particular space or a building type. Uh, the next is here. So Yashima, we have a question coming up. So based
Yeah.
on our previous slide, how I explained what are the uh, perimeter zones and core zones. So the question here
Yeah.
is,
Yeah. So the question is, in the image, which color represents the core zone? Is it red or is it blue?
this is going to be very simple. So for all the people who's looking at this, so these are your perimeter and core zones, and the one which is non-conditioned area that is depicted in white. All of those are car parking or the toilets, which uh, for this purpose we haven't shown it to explain it to you. Generally, however, when we do the energy modeling, we need to zone more or less all conditioned and unconditioned spaces. So,
Mansi, I would just like to clarify one thing. So when you mentioned about the perimeter zone depth, were you
mhm.
talking in meters or feet?
So that is roughly 12 to
Feet.
15 feet.
Yeah.
Yeah.
Okay. All right. All right.
Yeah.
I
So
will
then,
now end the poll. Here are the results, Mansi. 73% say blue and 27% say red.
perfect. So most people here are correct. Okay. So the core zone is blue. Okay, as we discussed earlier, because that is specifically at the core, because that is surrounded by perimeter zones on all the four sides. Okay. So the ones in red are the perimeter zones, and the one in blue are the core zone, and the white are, as I said earlier, that those are non-conditioned spaces. So first step for energy modeling is zoning the floor plans and creating a single line drawing based on the zone in the AutoCAD. That's the first thing which I do when I start with energy modeling. I start looking at the thermal zones, and I start drawing those thermal zones. So these thermal zones depend on predominant load in this particular space. As we said that predominated in perimeter zone, it is the external loads which takes predominance, while in the core zone, possibility is that the internal loads, so due to occupancy, lighting, and equipment, will be predominant. Again, I'm repeating this. This might depend on the kind of typology of building. So, say for offices, your internal loads are very high. So, when we worked on a project where it was an office building for a multinational corporation, their internal loads were pretty high. The equipment, so the IT equipment loads were very high. So we could see that even in the perimeter zone, your internal loads were predominant. So this is again based on case to case. Uh, the next step here is, once we have started looking into the thermal zone, the next step for us is creating an input data for energy model. So to build the energy model, we require two set of inputs. One is the external loads and the other is the internal load. For example, external gains, we require inputs like U value for wall, roof, emissivity of the roof. This based on SRI coating used, okay, and U value and SHGC of glazing. For internal gains, we require set point temperature and relative humidity to be maintained during hours. So that is set point temperature is the first thing, right? We do require that for all the spaces to maintain the particular set point. For internal loads, we have occupancy loads. So those are latent and sensible loads. These are calculated based on number of occupants in each zone. The second is the lighting loads. So lighting power density is measured from lighting drawings or assumed as per standards or codes that can be ASHRAE or Energy Conservation Building Code specifically for India. Ventilation rates, so these are calculated based on standards for each spaces. So each office would have a different ventilation rate as compared to a proper residential space. So you could refer to ASHRAE 62.1 or National Building Code 2015 version to get the ventilation rates. So those are nothing but a fresh air rates. Uh, and then equipment loads or equipment gains. These are assumed based on number of equipments and the type of equipment in each space. So as you can see, here is the example of internal load discussion with the client, which I had on this particular project. So for example, here you can see that in each the cabin, after discussion with the client, we considered occupancy of one person. So, this is an typical office space. Okay. Then there are cabins and there are often open office, conference room, lounge. But how do we ensure that we have estimated or assumed correct set of equipments as well as lighting assumptions in all of these cases? So what we do is we set up the calls with clients and architects on board to understand what are the client requirement, and then we start putting that together in sort of as a part of assumption sheet, and then we take that forward. So say here in this example, we are looking at cabin. So we discussed that, client said that, okay, we have one laptop and probably one printer in this particular case. And then we assume one more ceiling fan. And then we started looking into it. So that's how we came up with this set of assumptions. Okay. So, and again, so say for equipment, what we generally do is we conduct a small market survey and then assume the wattage of each of these equipment. So we consider printer, or say if the kitchen spaces would have kettle. So all of those we start looking into after doing this short online survey. So the next step is, started looking into schedules. So schedules are important. So, once we, so on the left here, you see what you see is a typical calendar. So in this particular office, there was Saturday, Sundays, all the Saturday, Sundays were off. So this is the calendar which we assume. On the right and the right hand side, you can see the schedules. So schedules are nothing but the operation time of the equipment, occupancy, and lighting across the day. So as you can see, we have assumed the lighting to be on across the day, but say say during the daytime at 0.25%, because we had incorporated daylighting sensors in this particular space, and they had it was pretty daylight. Similarly, and say we started looking at the lights which were on after 6 p.m. Same thing with occupancy. So we started considering, there say not all the people would be, coming into the office each day. So there is certain set of absence. So we accounted for that, and we accounted for the, afternoon break, lunch break, and then we started developing the occupancy schedule and the
Mansi,
equipment schedule. Yeah.
hi Mansi.
Hi.
Uh, can you go a little faster with some of these slides
Sure.
because I think
Sure.
we're falling behind on time.
Yes. Sorry.
Thanks. Yeah.
So this is sort of example of input data sheet which we created for energy model. The next part, so this is how we create a input data sheet. We can discuss this with clients and NEP consultants on board. So the next part is load HVAC load reduction with energy conservation measures. So once we have the energy model ready with certain envelope properties and internal gains, we check the peak cooling loads, and we ensure that that is in the range of 200 to 400 square feet per TR. And then we start looking into various measures, which are say envelope measures and lighting measures. And so then we start checking the percentage reduction which each of these measures, okay, provide in terms of system sizing. And say for energy efficient buildings or net zero buildings specifically, we target square feet per TR of around 600 to 650. So, for example, here what I have done is we have started looking into various glazing, roof, and wall measures. And on the so say on the x-axis, you can see percentage reduction in cooling load, and these are the various measures. So here you can see the percentage reduction in cooling load based on each of these measures. So yeah, as you can see, the wall, so window measures are more say energy efficient in this particular case. So because they offer maximum savings, because it is the reduction is due to both SHGC as well as the ULE, so conduction as well as radiation reduction. So then we start looking at the bundles. Then we bundle these measures together to come up with more energy efficient case. Sir, I can end now, and we can take up the incremental cost discussion next time if you want.
Um, I mean, if it's a quick thing, I think we can just go ahead and do it because it's important to discuss cost at this point, Mansi.
All right. So
So
the
yeah.
next, absolutely, I'll quickly go over it. So the other factor which comes into play is the cost of energy conservation measures. So when we discuss this with client, this is going to save your energy. They ask us that, it's okay, fair enough. It is saving my energy. It is saving my energy bill annually. But what is the additional cost of it? So because ECM will have an impact on system sizing as well as we saw in the earlier slides, and it will have an impact on so EPI of the building. So as you could see that earlier. So in order to account for uh, uh, energy savings in system sizing, we have a term called net incremental cost. So the where net incremental cost is nothing but the cost of ECM. For example, cost of DGU, installation of DGU, um, cost of DGU and installation of DGU minus the cost reduction in system sizing because of the load reduction. So say if the DGU costs say roughly around 2,000 rupees per square feet, there is significant percentage reduction, say almost 25% reduction in HVAC system sizing. So we account for that in this term called net incremental cost. So in this slide, you can see that I have shown two parameters here. The parameter in blue is the cooling capacity savings in cooling capacity, and the parameter in red is incremental cost. So the next step for me is I check the incremental cost for all measures and select the measures accordingly. So what you would see is for certain measures, the incremental cost is negative. So this happens. This means the system sizing saving is higher as compared to the cost of implementation of that particular ECM. So in this case, say for roof insulation of zero point 0.9, the shading 0.9, your HVAC system sizing saving is higher as compared to the cost of insulation. So there are certain measures like this, specifically like roof U value, or say for specific, this happens with shading measures if done correctly. So those ECM should be always bundled together. So yeah, so this is how we uh, do the system sizing correctly, as well as start accounting for the cost position. Thank you.
Great. Thank you so much, Mansi. We have a couple of questions. I'll take them on one by one. Our first question is, how do we decide the width of the perimeter zone and core zones while creating the energy model?
So generally, as a rule of thumb, we take our perimeter zones to be 12 or 15 feet. So that would be around 3 to 4 meters roughly. So that is sort of a thumb rule, which a method which we generally observe. So for perimeter zone, you would want or at least one side of it to be exposed to the external wall. So those are the ones which you call the perimeter zone.
Hey,
Right.
I
Mansi,
hope I.
the question was not depth, it was the width of the perimeter zone.
Sorry. Width of the perimeter zone. That's interesting. So
How do you mean width? I mean, it's really the depth of the perimeter zone that you
that
are
would make a
interested in.
difference.
Yeah.
Yeah.
So
I
can you go
think
to your slide and just show what you mean by width and depth so that it's clearer to the students?
I have
Sure.
a slide which might answer that,
Okay,
Sure.
cool.
Mansi. Yeah.
okay, great.
I can show you that. Okay, here is a footprint of a building. Let me just share my screen.
Yeah.
So let me know when you can see. Can you see my screen?
Yes.
Okay, but right now,
We see your task manager, we see.
right, how about that?
Yeah.
Okay.
Visible.
So here's a floor plate of a commercial building that we worked on some time ago. So there are three kinds of zones. Okay, so your slightly orangey zones are what we call the perimeter zones. So they are attached to some external wall. Okay. Then the blue ones are what we call internal zones. And sorry, Mansi, it's completely reverse, I think, to your color coding, but it'll do. And the unconditioned zones are your amenity zones. So toilets, kitchenettes, whatever it is. Now, the reason the engineer has broken it down in this case is because it's what we call a floor by floor system. So on each floor, there are air handling units, and they are treating these different zones. So you can see here, there is an air handling unit that is handling this perimeter zone. There's another one that's handling that, those two zones that we are calling north perimeter zones. There's a north arrow that's missing here. And these ones are more internal zones, okay? And if you were in India, then this would be a north-facing zone because the sun comes least in the north zone, and you can sort of consider it to be an internal zone. So in this case, the air handling unit is handling both an internal zone and in India, a north-facing zone. In India, the sun comes on the southern part of the sky, okay? So you can see that here as well. Here's a perimeter zone, here's an internal zone. And that kind of decision has to be taken finally by the air conditioning engineer, but the architect is able to just draw this, well, I guess Mansi said 12 to 15 feet, which is approximately 4 meters. So we usually look at 3.6 to 4 meters. Air conditioning engineers will look for that as being a perimeter zone. Okay. Sorry, Mansi, I took over your presentation a bit. I'll give it back to you.
Great, thanks, PC. I think that was definitely very helpful. I'll move back to our questions. So another question that we have, Mansi, is, are there any thumb rules for right sizing to do sanity check while calculations? Mansi, you're on mute.
Sorry. So there are sanity checks which you could do for HVAC right sizing. There are certain points which you should see, as I told earlier, that for say, if you want to see if your envelope is working well or not, what you could do is check the peak external loads of the envelope and compare that to the Griha benchmark. So Griha talks about peak envelope loads of 0.30 watt per square meter. So you could check that. That's the first step. And the second step is, say, for business as usual case. So for a case which is not energy efficient, you could do the square feet per TR check for the building, and that should come roughly around 200 to 400 square feet per tonnage peak cooling load for a particular building. So that is generally what you see here in India in terms of if the building is not energy efficient. So that is sort of a thumb rule which we have. And so if you want to see that if your envelope is working very well, if your then you check, I mean, for say net zero buildings, we see square feet per tonnage numbers of roughly around 500 to 600 square feet per TR. So those are sort of checks which we have to do, one has to do, to ensure that your energy model is working well. Because energy model are nothing but, so you have to be very careful with them. So it's not
Right,
necessary your model is giving out the correct result. So there has to be a check on each step.
absolutely. And a similar question on the costing aspect as well. So if there are any benchmarks to calculate savings on incremental cost or, overall HVAC costing.
There is no set of specific benchmarks, I would say, in these. That comes with experience, but I don't think there is one set of benchmarks. I think I would like
Right.
PC's input on this one.
There are some benchmarks that people use for central plant and for VRF type systems, but unfortunately they vary based on climate, because in certain climate zones you have you're generally faced with a higher watts per meter squared, or the reverse of that, which you use in India, a lower square foot per ton. And in other areas, you can have greater square foot per ton, or as we say, smaller watts per meter squared. So it's difficult to give you benchmarks that would be applicable across the country. You're best off talking to a supplier or talking to 2 or 3 suppliers and get what they provide you with, then you get a good idea for what they have.
PC in India, if you talk to suppliers, you probably get 150 square feet per ton. So
Yes,
I think you're really careful about talking to suppliers to get benchmarks in India.
that's true. I mean, I probably once you get that number, then you can halve it. Because you want to be at least 300 square foot per ton, according to Mansi, and that's, I think, right in the right ballpark.
Yeah, and that's for an energy inefficient building. I think for the students, what they are designing, they should aim for 600 square feet or higher for most building types.
Yeah, for office buildings. I don't know if you can get those numbers for other kinds of buildings, but certainly for office buildings.
Yeah. All right. Thanks, PC, for your inputs on this one. And thank you, Mansi, once again. That was all for the questions from for now. And if there are any, I'll maybe get back to you and respond to the students later on. And now we will move on to PC's
Thank you.
presentation. PC, you can go ahead and share your screen.
I will, but I want to say thank you, Mansi. It's always a pleasure to do the my bit after what you say, because I have to do very little explaining. I can go straight into the how to model it in Design Builder. This was really good. So what we'll do is we'll just follow up on what Mansi talked about and show you how to put those things through in Design Builder. Let me just share my screen. Okay, I'm just going to put a couple of quick slides and then we'll go from there. Okay, not that one. So if you guys remember what Mansi said, a summary of that is internal and external gains is really in this chart here, okay? So the building loads are basically solar radiation, or what comes in as sunshine, what you're generating inside the building, and Mansi said lights, equipment, people, these things make heat. Then temperature difference, so there's a temperature outside, you want to maintain a temperature inside, and therefore Mansi said you're using U values to mitigate heat transfer. And then finally, there is air exchange. So you have infiltration, which is poor quality construction. So it leaks, ventilation, because you're putting air for people in terms of ventilation. So how do we define these things in the energy simulation? Again, Mansi has told us we specify these numbers. We provide a schedule for how they are operating. And the model then uses that to calculate a cooling load. Now, one thing I do want to say, which I guess, we use the terms gain and load interchangeably, okay? And that's how it is in common practice. But as when you're looking at air conditioning, the air conditioning engineer is very clear that something is called heat gain, which is instantaneous. So if you switch on a light and the light is 28 watts, then you get an instantaneous heat gain of 28 watts into that space, okay? If you turn on a fax machine, then whatever the fax machine is using in terms of heat, it's an instantaneous gain into the space. But what the air conditioning system sees is not the sum of the gains at any instant. And that's because there is storage and release of heat in the building fabric. And that's why we need energy simulation or load calculation methods. Because when you add up the gains, they don't translate to cooling load. They translate to cooling load in a slightly different fashion. We talk about that being a fast Fourier transform where you put in a pulse of heat gain, and then you watch the decay of that heat gain across time, and that's what the air conditioner has to meet. So that's what you're doing when you're calculating heat load or cooling loads, I should say, okay? So when we are doing energy simulation, what you are specifying is the elements that provide heat gain. So all those things that we saw in this graph, they're all the elements that provide heat gain into a space. And then the program computes the cooling load, and that's what you do. So let's go straight into Design Builder. And I've got a model that I've set up because it's not going to be able to, we won't have the time to go from scratch. So let's look at each of these, okay? you know how to do constructions. We showed you how to do that last time. So that gives you U values. You know how to specify window performance properties. So that gives you solar heat gain coefficients and U values. Okay. What about the rest? Well, if you, and of course, you can set each of these things for each zone. But the way to probably do it best is you take the default bits that are applicable across most zones, you enter those at the building level, and then you make changes at the different zone level. In fact, as you get more expert, I suggest that you build templates. So for example, you might want to build a template for office areas, and then another template for amenity areas, and so on. Okay. And those are things that you can think about. But I will show you now where those gains can be specified. So if you go to the activity tab, you can take care of some of these gains. Okay. So the gains we're going to be looking at is, the first one is going to be occupancy. How many people are in a space? Okay. So you have 2 or 3 ways of specifying how you can provide these gains. And if you go to this model options spanner, you can change how this is represented. Okay. So you have here occupancy method, and you can see here I've said area per person. So I have said 10 square meter per person. Okay. Now, typically, those the number of feet or meters per person is set by the National Building Code or some standard or the other. Okay. And I've seen numbers in India which are 8 square meters per person or 6 square meters per person. So depending on what type of activity is happening in that zone, you have to find the correct one, find the number, and put that there. Other options are available. If you want, you can say how many people there are, or if you want, you can reverse it. Instead of how many square meters per person, you can say how many people per square meter. So you get a fractional number. But I find this area per person is probably your best bet. You have similarly options to provide for lighting and for equipment. You can see it here. And in both cases, I have set it as power density. So it is watts per meter squared of power density. Anyway, let's go back. Let me show you the people. So this is how many meters squared per person, but you're also telling the program how that varies across the day. Okay. So this 10 meters squared per person is your maximum design occupancy. And your schedule, which is this one, which I'm going to open right now, will tell the program how does that heat load vary across the day. Because when you're in a building, people will come in, stay for a time, leave after a time. And the heat load from people will obviously depend on how many people there are in the space at that time. I should say the heat gain. Sorry, I also make the same mistakes. But it's the instantaneous heat gain we're talking about. Now, I've got some 3 or 4 different schedule bits here. So there's one for the design day, there's one for the weekday, there's one for weekends, There's one for holidays. And as you use Design Builder, you can certainly set up your own. The cooling load calculations will use the occupancy schedule for the summer design day. And that is when the engineer actually takes a pick and he says, well, for my design day, which is like a worst day of the year, this is how I expect people will occupy the building. This is how the heat gains will be. And that's what he's looking for. Okay. So that is for people. Okay. Now, there is a third underlying thing that we don't generally talk about, but it's there in the background. And that is that how much heat does a person actually release? Okay. And again, there are standards for different locations. Here I'm using a number that is provided to me in Australia by the Australian Institute of Refrigeration, Air Conditioning and Heating. You have got numbers from ASHRAE generally and ISHRI, which will tell you how much to use. So in this case, the heat rate per person is a 130 watts, and that's a total of the sensible plus the latent heat gain from people, instantaneous heat gain from people. Now, I have a fixed fraction of that, which is 42%, 0.42. So 42% of my 130 watts is actually latent heat that a person is providing. And if you do the maths, you'll find that sensible is 75 watts, latent is 55 watts, and that's how we get the 130 watts. Okay. Now, you don't need to give any other things for calculating the cooling load, so I'm not going to worry about the others. One thing you do need to do is you do need to provide a thermostat temperature that the air conditioning system is going to be aiming to keep when it is calculating the cooling load. So it needs to know what temperature am I aiming for on the inside. Really speaking, you should also give the humidity, but typically it will self-size to around the 50% relative humidity, and that's quite fine. Okay. So here my cooling thermostat is set at 23.9 degrees. Okay. I'm looking for about 24 degrees, so I've set it just below 24 degrees here. Okay, the next thing over here that you need to do is put your office gains. Now, what is your office equipment gains? Printers, fax machines, zip boilers for hot water, anything else in the office that is making heat, right? So the total load that I'm using is 11 watts per meter squared. And again, that is a number that we use commonly here. Again, GRIHA will give you numbers. GBCA will, the IGBC will give you numbers. LEED will give you numbers, and they will give you numbers based on what type of building it is and what activity you're doing in those buildings. Same sort of thing as in for people. Your 11 watts per meter squared is your maximum design equipment load when everything is switched on. And then your schedule is actually going to decide how that equipment varies across the day. Okay. And just as before, I have got here something that accounts for the summer design day. In this case, my weekday schedule and my summer design day schedule are the same. So I'm using the same schedule for both those days. Okay. And then I've got weekends and holidays and all those other things, which we did when we did schedules before. So you might want to go back and revise that. Okay. So 2 out of 3, the one that's remaining is lighting. And lighting is not on the activity panel. In the lighting panel, what you can do is you can give a target illuminance level for daylight or light, okay? And the reason is that, like Mansi was saying, they changed the schedule because they're using a sensor, a daylight sensor, to manage the amount of electricity being given to the lighting system. Now, with Design Builder and Energy Plus, you actually don't need to do that. You give the proper lighting system watts per meter squared. And here I have 4.5 watts a meter squared. And I give it a lighting schedule, which means this is how that maximum design lighting gain is going to work across the day. And again, you can see my weekday schedule and my summer design day schedule are the same. Okay. When an air conditioning engineer calculates the cooling loads, generally, he doesn't account for daylighting. He says that typically I want to be sure that my system has got enough capacity to provide cooling on the worst day when everything is on. Never really happens, but due to legal reasons, he may decide to do it in that conservative fashion, okay? But in your energy simulation, not your cooling load calculation, you can actually switch on lighting control, and you probably want to do that only in the perimeter zones. And when you switch on lighting control, you can go and have a look. There are some 3 control strategies that are available. But as soon as you switch on this lighting control, you'll find, if I go to any of the zones, I'll find that it has attached a light sensor to this zone. Okay. And then using that control strategy, you can calculate the energy use, not cooling load, but the energy saving because of using a lighting sensor. Okay. I'm going to go back and I'm going to remove that so we don't mess up our cooling load calculations. Okay. So we have now dealt with people, we've dealt with lighting, we've dealt with equipment. Okay. What are the other ones? Well, there's ventilation and infiltration. Okay. So let's do those 2. When you're looking for ventilation, in the activity tab, there is a box called minimum fresh air. That's your ventilation load. Okay. And you can set it in 2 ways. You can set it as a liters per second per person. So in this case, I've got 10 liters per second per person ventilation. You can either add or you can specify liters per second per meter squared of floor area. Okay. Now, when you actually do the calculation for cooling loads, it will add these 2 numbers if you put a number in this area number. If you leave it as 0, then it will only take the liters per second per person. That's your ventilation load. Your infiltration, which is leakage and so on, you'll find that under construction. So if you go to the construction tab, you can set infiltration rate for each zone individually. And what you'll typically find is that in many codes and standards, ECBC, GRIHA, IGBC, they will set a lower infiltration rate for internal zones because you're not connected to the outside. And they will set a higher infiltration rate in the perimeter zones. So you have to find out what it is and apply it. Now, typically around 0.7 air changes per hour at atmospheric conditions is typically what we do here for commercial buildings. You may want to find out what it is for each different kind of building in India. Okay, and there will be guidelines available. There'll be resources available for you to do that. Okay, so we've done infiltration as well. The remainder you've already done. I don't need to do that. Solar radiation is basically the solar heat gain coefficient from your windows. Temperature differential is U values for all your construction materials. You've done all of that. So we have done specifying all the internal loads or internal gains for your simulation model. Okay. Now, the way it works is that the model will run. It will take this instantaneous heat gain, everything that you specified, and then it will work out what is the actual cooling load, which will be different from the instantaneous heat gain. Okay. If you have a lighter building, then the heat gain translates into cooling load quicker. If you have a building that's got a higher thermal mass, then this heat gain translates into cooling loads at a slower pace. Okay. All right. So let's do a run. That's probably the easiest way to understand where we're going. Now, I did talk to you about the fact that these calculations are done for a design day. Okay. I have chosen Bangalore here. And if I go to Bangalore on the top, I've renamed it. You can do that too. If you go to the location tab, you'll find here summer design weather data. And what I've got here is I have set it to multiple design months. I've chosen the most stringent design day. So if you look at my design day, here's the monthly maximum design day dry bulb temperature. So the peak temperature of the design day. And you can see here, April in Bangalore seems to have the highest temperature of 35.2 degrees centigrade. Okay. At that time, the wet bulb temperature is 19.6. And if you look up a psychometric chart, you can see where those 2 points meet. That's your design condition for the maximum point. Now that happens at about 2 o'clock in the afternoon on the solar noon day. Okay. And the program works that out. But the way it works it out is it also wants to know what's the minimum temperature for that day. So it puts a sine wave curve through that, and then it works out the how the temperature is varying across the day. And because of that, this combination of stuff, that is how your building works, what you're doing in the building, how is the sun responding to your building, did you do good shading for the peak day, all of those things come into the picture, and it starts to give you some cooling load numbers. So I'm going to make a cooling load run, and you do that by going to cooling design, running the model. And here what I've done is I've picked the 21st day of the month to do this cooling load calculation. And I've said, make a cooling load calculation for each of the months. So from January to December, it will run one summer design day. I haven't put any design margin. Now, Mansi was talking about design margins. ASHRAE uses a 15% margin. And I've seen that in India as well, they do that. We don't think you need that much margin because, you know, what you're using is called a heat balance load calculation equations, they are very precise, okay? But engineers always want to be conservative. My guess is that I would be quite happy with a 5% margin, okay? But don't listen to me, listen to whoever is giving you advice on HVAC. So I'm going to run this, and what it will do is it will make 12-day runs. So you'll see them flash past. January, February, March, April, May, June, etc. And then it'll give me cooling loads. And when you're in cooling loads, there is another interesting thing to be aware of. So here we go. Give it a few, it will take less than a minute. It's a small building, so it takes very little time. But as your buildings get more complex, there are more surrounding buildings, there are more shading elements, then this calculation can take longer time. So don't be frustrated. It does take some time to happen. In this case, you must let the results load completely and display, okay? So we'll give it a few minutes, it'll finish up. While it's doing that, I have set up files for a VRF system and files for a VAV system. I'll show you that and explain to you how the loops work. There are 2 or 3 webinars now available where there is an introduction to detailed HVAC in Design Builder, and I'll give you links for that in a second. So here we are, we're almost there. And the calculations are incredibly complex because for every surface, it's doing a calculation. For every zone, it's doing more than one calculation, okay? Okay, so these graphs look very nice, but what we'll do is we'll go look at the numbers, which are under summary. And if you look here, what I've done is, these are all the zones, and you can recognize them. I've put the unconditioned zones out of the cooling requirements, so there's no cooling load there. But any heat gain from those zones is passed on to the nearest zone, which is conditioned, okay? So for this building, my total capacity for the building right now is this 207 kilowatts, okay? But this is what we call the sum of the peaks, okay? And if you look here, you know what I mean. Each of these zones peaks at a different time. So this zone is peaking at 2 o'clock in the afternoon in December. This is peaking in March. This is peaking in June, okay? And that's a function of orientation, thermal mass, glazing, shading, what's happening inside the zone, okay? And what that means is that because all these peaks are happening at different times, I don't know what's the total building peak at any one instant, and what is that, okay? That I will know if I say coincident building peak, and you can see here it says 179 kilowatts. And that's happening at 4:30 on June. Okay. So that's when you start to have to understand a bit more about air conditioning systems. If you are designing a central plant, your chiller only needs to be 179 kilowatts. If you are designing split systems, then it gets more complicated. If you have one split system in every zone, then you need to go back and look at the peak at each zone. So for this zone, the peak is 12. You need to have a 12 kilowatt system for that zone. If you decide, no, I'm going to build a cooling system where I have a VRF system for each floor, which is what I've done here. Then if I look at the sum of the peaks, it's 54 kilowatts for the ground floor, 73 for the first floor, 79 for the second floor. This has a roof load. This is a typical floor. This has the ground that it's sitting on, which mitigates the amount of cooling that's required. Okay. But again, you can see here that each of these zones is peaking at a different time. But if you want to size the outside unit, the condenser unit, you can say, show me the coincident loads for each cooling system, and then it'll tell you what is the size of the external unit for each floor. Okay. Mind you, that's the external unit. The internal unit for each zone will have to be the peak for that zone. Okay. If that's confusing, it's quite confusing to a lot of experienced air conditioning engineers as well. But that is how you make efficiencies within an air conditioning system. And there are some resources available to find out about this. Anyway, I'm going to stop there. So this is your cooling load exercise for how to calculate cooling loads. Now I've got a few minutes. So I want to quickly show you how a VRF system is set up and how a VAV system is set up. Now on this one, I have actually got the VRF system. I've just hidden it. So if I unhide it, and all I need to do for that is to change the air conditioning from simple to detailed. And I've left it here at simple HVAC data. Okay. There's quite a lot of, you can put detailed HVAC data, but you should only do that when you have real reason to do that. If you want a temperature thermostat schedule that's changing all the time, yes, you need to put detailed HVAC data. But if you've got a fixed thermostat, you don't need to do that. And sometimes it's easier to do that. Read up just on the help file, go and read up simple HVAC data and detailed HVAC data, and it'll give you a table explaining why you need to do which. Okay. So
PC, I'm sorry to interject, but the chiller and VAV system is something that we would do in the next session.
Okay, then that's easy. That gives me a bit more time to do VRF. Okay, thank you.
Yeah, we'll spend some like a separate session on that because it's slightly complicated and we don't want to rush through it. So
thank you. That's great. Okay, so
but I mean, if you want to like do a brief intro or something, that's fine. But we'll invest more time on it on a separate session.
Yeah, I think there's only about 15 minutes left. So let's do the VRF with some detail, and then we can do the chiller on the next one. Is that okay?
Sure. Okay. Yeah, that sounds good. Okay.
Okay. So what I did is, when you turn on detailed HVAC, you get a drawing pane for air conditioning systems. Okay. And I've set it up already. I'll show you how I've set it up, and then I'll show you how you can start drawing these systems. Okay. So you can see here, I've got now a representation of the air conditioning systems, and I've got a representation of the geometry of the building. Okay. So I've got 3 outdoor VRF systems. These are the things that you see on the rooftops or balconies or whatever. They call them ACCU sometimes, condensing units other times, outdoor units other times, all fine. Any of these work. So I have 3 outdoor units. Each outdoor unit is for a floor. So I've got one for ground floor, first floor, second floor. Okay. And then I've got this thing called a zone group. If I click on this zone group, you can see how many zones are here. So this zone group has got 6 zones in it. Okay. And in each zone, there is a fan coil unit. There's the head that you see inside the room. It could be a cassette, could be something on the wall, could be something under a bulkhead, which is delivering cold air, but they all do the same thing, right? In most countries, you will have a cooling coil and a heating coil. In India, you get both. You get cooling only machines and you get reverse cycle machines, okay? There is a fan. This fan is what is drawing the air through the cooling coils and pushing it out into the room, okay? And you can see here there's what we call a mixing box. So this is where it is picking up ventilation air, 10 liters per second per person. It's coming through here for this zone. And whatever it's picking up, it is exhausting. And the rest it is recirculating. So that's the job of the air conditioning system, okay? If you make any changes, you have to apply it to all the zones in the zone group, okay? And that's quite easy to do. You can keep double clicking till you get to the component that you want to play around with. So for example, if I want to edit the efficiency of the fan, I can do it here. When I finish editing those details, then basically I need to make sure that I have edited it for all the different zones in that zone group. So you go to the target and you basically say all zones. Okay, so any change you make needs to be effective to all the zones in that zone group. Okay. If you look, and that's how you work on the zone group. So obviously, the first thing you need to do is you need to create the zone groups, assign all the zones to the correct zone groups, and there's a procedure for that. Okay. And there are 2 very recent webinars that Design Builder UK has put out. I suggest you can go and find them and please register and watch them, okay? So if you go to DB UK, so that's basically just designbuilder.co.uk. Under training, there are webinars, okay? And these 2 are brand new. They're only a few months old, so they can now have got a lot of the latest things that Design Builder has. Advanced HVAC system modeling. Probably see this one first, modeling HVAC systems from concept through to detailed design. Then look at advanced HVAC modeling. So what I do next time will help you if you watch these 2 webinars and come. Okay. All right. So I'm going to quickly look at the outdoor units. Okay. So if I go to back to the drawing of the whole system, if I look at any of the outdoor units, and I can do it either from here or from here, it doesn't matter. What you'll see is that there is quite a comprehensive description of these systems, okay? So unless you really understand what you're doing, the defaults are actually pretty okay for the VRF systems, okay? They have got COPs for cooling over here. They have a bunch of curves which looks at the outside temperature, the inside temperature, the amount of capacity of cooling that it's delivering, as compared to the total amount of capacity it can provide. And based on all of that, it works out the COP at that point. And what is a COP? It's simply for each unit of electricity that you put into the condensing unit, the outdoor unit, how much of thermal cooling it can provide. That's the 3.3. So at design condition, it will provide 3.3 kilowatt hours of cooling for every kilowatt hour of electricity that you put into the compressor. Okay. Similarly, if there is a reverse cycle heating, then there is options here for the heating. And you'll find generally the heating COP is slightly higher than the cooling COP, because in the case of heating, all the heat from the compressor will also do useful work. In terms of cooling, you're throwing away all that heat. Okay. So again, you have curves, same sort of thing to do that. Now, VRF systems have got a heat recovery mode. Now, that doesn't really, it's not really very useful in a cooling only situation, because in a case of cooling only in a hot day, you're never going to have one zone that requires heating and another one that requires cooling. So that's quite irrelevant for most places in India. So don't even worry about it. Just leave it and do what you need to do. Okay. It will do the runs. It will model the energy use. I've already done a run, so I will share the results for that. Where am I finding? Oh, here we go. So here is an HTML output for that. Here we go. So this will be the summary outputs that you get. You can search by topic, and depending on what you ask for, it will give you a whole bunch of reports. So here I've asked for some DX reports, some cooling coil reports, some fan reports, some ventilation loads, what is mean air temperature in each of the zones. So whatever I've asked for, it's given me. The simplest, what you might be looking for, is really the energy use numbers. And here you can see the energy use numbers. There is very little cooling, in fact, zero cooling for an office building in Bangalore. Sorry, zero heating, I should say, not cooling. So certainly a lot of cooling required. And you can see here how much energy in electricity terms it is using to provide cooling. There is lighting energy use, equipment energy use, fan energy use. Okay, so those are the main things that you're looking for, and Energy Plus will do those calculations for you. And obviously, you can go and check anything else that you might be interested in. So there are some peak electricity meters and so on. There are coil units, and you can look at them. So it will tell you the total cooling coil energy. These are thermal energy numbers, not electricity numbers. Electricity is what you saw in the table above there, but you can see all the things that it puts out for you. Okay, I think we're almost out of time. So the last thing I want to show you before I close off is how do you get started? And the way to get started is when you get to this system, you can ask for it to load an air conditioning template. And when you ask for that, you will find that there's a whole bunch of predetermined or preset templates for air conditioning systems that are already built in. And what you do is you pick a template that's closest to what you want to model. Take that, it'll give you a rudimentary system, and then you modify that to your needs. So whatever template it gives you, that'll run. Okay. So if you just apply a template, you go save and you hit simulation, it will run. Okay. So Design Builder tries to make it easy for you. There are, let me cancel that. For other systems, not for the VRF system so much, you will find yourself putting a lot of controls and looking through how to connect things and then providing control strategies for each component. And that is quite complex. You may need to speak with a mechanical engineer to understand what to do. We'll show you the basics for a VAV system next time. But for a VRF system, it's fairly straightforward. You simply connect an outdoor unit to a number of zones in the zone group, and it takes care of the control strategy between it. You need to provide within the building level, you need to provide the thermostat settings, which we've already done. And of course, all the other gains that we talked about. So the fresh air, the thermostat setting for cooling and for heating, if you're interested, they need to be provided. And then the model will take care of the rest. It looks simple, it isn't. And as you start using it, you'll find yourself making mistakes or the model not working. You'll have to go back and correct them. Once you've got it right, then things will start to come. Just because you're getting some answers doesn't mean those answers are necessarily right. If you have made any errors in your input, like we say, garbage in will give you garbage out. So you have to be very careful in putting your materials, your construction, your windows, your shading, the material that you've got in your construction, and all those internal gains we talked about. Okay. So Yoshima, I'll hand it back to you. If there are questions, we can deal with them now.
Sure. Thanks, PC. So our first question is, why can you explain why did you select 21.1 degrees Celsius instead of 21 degrees Celsius for heating? I think this was in the beginning of your session.
Yeah. Don't worry about that. The reason we do that here is we are mandated to test between 21 and 24. And because these calculations are iterative, so you are aiming towards a solution which is iterative. In some instances, you may get 19.999 and then, oh, sorry, I should say 20.999, and the system will think that's 21 is okay. But when we are actually doing an Excel sheet calculation, then it'll say, no, you didn't make it, so it's 1 hour where you didn't make the temperature. So to avoid that, I've just put 21.1 and 23.9. You guys put what you are aiming for, and that's fine. Okay.
Right. Thanks, PC. Next question. What is the difference between lighting power density and normalized power density?
Okay. So that's only a way that people, let me just share my screen. It's a way that some systems like to account for it. So for example, if I go to the lighting tab here, and right now you can see it's watts per meter squared. But if I say, give me normalized lighting power density, then the unit that they use is slightly different. So let me put it, it's the easiest way to explain. It will be the lighting power density per 100 lux that you're aiming for. Now you remember I put 320 lux as the target. So it's using that to work out some number. So this just means that it's 5 watts per meter squared per 100 lux of actual light on the working plane. Now you'll find LEED has got a normalized lighting power density that it looks for. So people who are doing LEED projects, they may want to use normalized lighting power instead of watts per meter squared. It's just a way of representation.
Right.
Okay.
Thanks, PC. Next question. Can we consider power density values from ECBC for simulation based on the ECBC compliance category?
Absolutely. That's exactly what you should be doing.
Yeah. All right. Next question. Which standard will we use for selecting the value of infiltration on the construction side?
Okay, I would be guessing that it's your NBC, your National Building Code. But again, I'm not sure. Sometimes the codes themselves have got numbers that they want you to use. So it could be different for each of the rating systems. So GRIHA may have a different one from LEED and from IGBC. So you may need to read the documentation to decide what's the correct one.
Right. Also,
Yashima,
yeah, Prasad.
on this one specifically, it might be good to have the team contact Nikhilesh Bist, who's a TRG member, and he has done a fair amount of work on infiltration rates. So he may be able to give better answers specific to the Indian context.
Yeah, and maybe he can give, if you're designing different types of buildings, you may find that there may be a slight difference in infiltration rates as well.
Sure. Yeah.
Right. So Nikhilesh Bist is one of our TRG members. You can contact him through the learning management system. Prasad, is it okay to give his email ID over here?
Sure. Yeah.
Okay, I'll just put it here in a while. All right. Next question. What is the meaning of summer and winter design day?
Okay. So if you missed it, when you are designing a air conditioning system, you are designing to maintain some particular weather condition outside. So what you're saying is that at this weather condition outside, my inside should still be this temperature. So say we are aiming for 24 degrees when we are doing cooling. Now you can't design a system which says no matter what the outside temperature is, my system will have to be able to deliver the capacity required. That is like saying I must have an infinitely large air conditioning system to do this. So instead, what we do is we look at historical data. Again, now that there's a debate going on about that, but that's a different question. But we look at historical data and we say, what temperature was not exceeded for more than 1% of the time in a year? And we call that a 1% confidence level, okay? And if you noticed in my screen, I was using a 0.4% probability or confidence level. So what we are saying is that according to the previous 10, 20, 30 years weather data, this temperature and humidity combination was not exceeded by more than 0.4% in a year. And therefore we are designing for that size.
Right.
And the reverse is true for heating. So, yeah.
All right. Thanks, PC. Next question. Can you explain about the COP values in the HVAC section and how we determine these values? Also about the schedule in this part and how these are different from other schedules.
Okay. Now that's a very good question, very complex question, but I'll try and answer that. So the COP value that you are putting into the simulation, into the description of the air conditioning system is an instantaneous COP value at a design condition. Okay, so you'll have to find from the manufacturer what COP is there at the design conditions and then put that in. Okay, typically there is an ARI test condition, and if it's done to an ARI test condition, then you can be sure that that COP is well represented. There are other COPs that they give you higher numbers, so your system looks more efficient, but in reality, that's not the case. So you have to be a little bit careful about that, okay? Try and get manufacturers' technical data sheets and ask for ARI test condition COPs. Okay, that's one. Okay. Now, what the schedule is doing, as I said, is that instantaneous heat gain, the maximum instantaneous heat gain from, say, lights. Okay. So if your lighting is designed for 4.5 watts per meter squared, when you switch on the lights in the room, then it is generating 4.5 watts per meter squared of heat. But that's all the lights, okay? The schedule is saying how much of the lighting system is switched on at what time. So between 8 o'clock and 9 o'clock is 60% of the lights are on. Then you put 0.6, and then it works out what is the heat gain from lights for that hour, and then for the next hour, and then for the next hour. That's the second thing. Now, those schedules, typically the schedule that the air conditioning engineer uses to calculate the peak load is sometimes a little bit more conservative than the way you may want to do an energy simulation, where you take more average kind of values. And typically this works really well for how people occupy an office. Very rarely do we have 100% of the design occupancy of people in a building. Typically you have 70 or 80% because 20% of the staff are at site or have taken a day off or are working from home or whatever it is, right? But the air conditioning engineer is always interested in, when you size a piece of equipment, he wants to be sure that if all the people were there, all the lights were on, all the equipment was running, and it was the worst day, the design day, then his system has got enough capacity to meet the temperature on the inside. That's why he's doing this complex cooling load calculation. So in Energy Plus, and that's one of the few programs that can actually do that, you can set up two schedules, one for the design day calculation and a separate one for the normal weekday calculation. So you can size a system which is bigger than required, which will manage the design day, use the same system to run an energy simulation where the actual occupancy will be less. And that will give you a really good representation for the energy use of a building, because that's how buildings work. Okay. In most other programs, you actually have to do them as two separate runs. You have to do a sizing run, get the sizes, feed the sizes into the energy simulation, and then write a separate schedule for the energy simulation run. In Design Builder / Energy Plus, you can do all of that in one run if you know how to do it well. Hopefully I've answered all of those questions.
Yeah, I think so. All right. Moving ahead, next question. Can we model a DOAS system, which is DOAS, with VRF in Design Builder?
Actually, you're very lucky. The default template for VRF actually includes a DOAS system for it. The way they have plumbed it is slightly different, but I'll show you that. So if you take the template and you ask for the VRF default, so this one comes with a heat recovery, and so you can see that here. That's the outdoor condenser. That's the inside the room system. That's the DOAS. So there's an AHU that's doing the dedicated outside air. You can add heating and cooling coils and controls here the way you want it. Right now, it's modeled for heating, so it's modeled for a winter climate, but there's nothing stopping you from putting a cooling coil and removing the heating coil from here. So your DOAS is ready to go. In this case, they have a heat recovery wheel already there, which you can specify. You can specify the efficiency of that wheel as well. So already ready for you to do. You just have to pick it up and work from there.
That's great. Thanks, PC. Next question. In the HTML output file, where can we find total / peak cooling or heating load?
Okay, you don't want to use that. Okay, there is a heating and cooling load there, but it's generally built for the coils only. You have to do the cooling design run the way that I showed you to get the cooling loads. Okay, and you do that cooling design run before you build the detailed HVAC system. You can do that at a very early age, a very early stage, and get those numbers. There are a few tricks as you go through. Hopefully you'll find them. You have to assign, let me show you. Here we go. So on the HVAC tab, okay, on each of these zones, say the north zone here, this is a ground floor zone. So I have created a series of cooling systems. So you can see here, ground floor VRF, first floor VRF, second floor VRF. So I have assigned each of these zones to the correct one. So this is first floor. So I've assigned first floor VRFs here. This is second floor. I've assigned second floor VRFs here. I haven't actually told the model how these things are working, but I've just assigned each zone to a particular system. So when you do the load calculations, it will calculate those loads correctly for you. Okay. You need to do 1 or 2 runs, and then you start to understand all the complexity behind it, and you start to get a feel for how to do that.
Right. All right, next question. What impact does a blow-through and a draw-through fan position in ADUs have on energy consumption? I think, yeah.
That's a very HVAC specific question. I don't think it requires an answer in an energy simulation class, probably for an air conditioning design class. So maybe we can move on from here.
Sure. All right. Also, going back to the HTML question, a follow-up question is, where can we find the value of roof, wall, and windows total heat gain?
Oh, I see. Okay. Actually, that is already available there. Let me see if it's still here. Oh, I did win. Okay, let me run it while we are talking. But what I didn't show you was that there are a number of columns to the right of what I showed you. Okay, we'll have a quick look because I was rushing a bit because I wanted to cover the VRF as well. So your check figures will be there, as well as the gains from each of the building elements. So it actually will show you how much comes through the window as solar gain, how much comes through the wall and the roof as conduction, convection, what are the loads from infiltration. It shows you all of those things. And it shows you check figures in metric. See, in India, we have this strange combination of some things are metric, some things are imperial units. So square foot per ton is definitely not metric. So it's a little, you have to use an Excel sheet to do the conversion. But all of those are already there. Let it just finish, and we can show you that. Meanwhile, do you want to ask the next question when it comes up?
Sure. Yeah, we have one more question. There's a question that this person has been putting in schedules, but they are not really reflecting in the results. So is there some hack, or if the results are not, the input parameters are not actually getting reflected, is there some hack to figure that out, or how to go about it?
If the schedules have been correctly input for weekdays, then they should reflect. Now, what's a hack to do that? The hack to do that is, if you look at the hourly lighting loads in the ESO file, you will see whether they are varying the way they should be or not. So that's probably the best way to do it.
Okay. Yeah.
So here we've got this. I'll just quickly show. So as you can see here, it actually shows total cooling load.
PC, you're not sharing your screen.
Sorry, apologies. Hang on. Yeah, so it just finished the cooling load calculation again. So you can see here, here's the total cooling load. This is adding the 5%. Design is total cooling load multiplied by 1.05. Okay. But that cooling load is without any oversizing factors, and that is broken up into sensible and latent. And if you look at the internal zones, you'll find that this sensible latent split is higher because internal zones have no solar radiation loads. And then you can see that it has met the thermostat temperature. This is the humidity it's calculated. Then if you go to the right, you will find all the other bits and pieces. So here's your check figures, liters per second per meter squared, and watts per meter squared. And you can convert this into your square foot per ton from this number. Now, watts per meter squared for us, when this watts per meter squared in metric is smaller, that means it's a lower cooling load. When you do square foot per ton, you want a bigger number. So it is handling more square feet per 1 ton of refrigeration. So it's just a representation of the way that the check figure is. This is the outside air temperature at that time, and this is what you're looking for. So how much energy is being gained or lost? Let me pick. Okay, this is the west zone on the first floor. And you can see here gains from glazing. And if you go to, so that's conduction gains from glazing. Conduction gains from the wall, conduction gains or losses from the floor, ventilation gains, infiltration gains, equipment gains, lighting gains, and there'll be people gains, and this is solar radiation gain. So you can see on the west, you're getting a very large solar radiation gain, okay? This will give you, this is again, if you're going into mechanical design, this will give you the fresh air ventilation rate. So it is 33 liters per second. That is 5% of the total supply air. The total supply air is given right here. It's this number. Actually, it's actually this number minus 5%, because here they've added the 5%. So pretty much everything you need is on this table. Okay.
Right. And one last question, PC. How do we calculate RETV values in Design Builder? RETV is the residential envelope transmittance value.
Oh, yeah. That's the new, that's the equivalent of the ECBC in residential. Yeah, I've just got the booklet. I haven't read it. But my guess is it's a bit like what they used to have in Singapore many years ago, which was called an OTTV. And so it's a envelope transmission value. I don't know,
Yeah.
there must be an equation in the booklet to do that.
Yeah,
And that
so
will generally it'll be something to do with the U values and the cooling load of some sort. Yeah.
right, right. So as of now, design builder obviously would not calculate that. It has to be done by, the user itself and maybe fed into the software.
Yeah. Those are
Right.
all very regional and country specific values. So typically design builder or programs like design builder won't give you a standard calculation for that.
Right. Yeah. All right. Yeah, that's all for the questions that we have, PC. And we have certainly gone over time. So this would be a nice time to close. Once again, thank you so much for your presentation. And I'm hopeful that our participants would watch the 2 videos that you've mentioned on the training that have just been launched, so that it's easier for them to understand the advanced module that we do next time. Thank you so much, and we will all see you next week. There's a webinar coming up on your deliverable 3, so you will soon get the joining details. And yeah, bye bye. Thank you.
Thanks.
Thank you. Bye-bye.
Thanks, Prasad. Bye.